In this video, I'm planning on talking about specific heats. So we already know from chemistry that a specific heat, well, basically we already know that it takes different amounts of energy to raise the temperature of identical masses of different substances by 1 degree Celsius. So let's say, for instance, if we have like 20 kilograms of water and 20 kilograms of iron. It's going to take and let's say that we want to raise this 20 kilograms of water by 1 degree and the 20 kilograms of iron by 1 degree Celsius. We already know that it's going to take different amounts of heat to raise the temperature of the water by 1 degree Celsius than it is the iron. So basically what the specific heat is, it's the property that allows us to compare the energy storage of different substances. So basically the specific heat is defined as the energy required to raise the temperature of a unit mass of a substance by 1 degree Celsius. So in thermodynamics, we're interested in two types of specific heat. The first one is C sub V, and this is equal to the partial derivative of the internal energy to the temperature at constant volume, and C sub P is equal to the partial derivative of the enthalpy to the temperature at constant pressure. So one thing to notice is this one has, so the C sub P has, we're taking the derivative of the enthalpy with respect to temperature at constant pressure. So if we look at enthalpy, we know that enthalpy is equal to U plus PV. So delta H is equal to delta U plus P delta V plus V delta P. But we know that this is constant pressure, so this is V delta P is equal to 0. So this is because this is constant pressure. So because of this, C sub P is always going to be greater than C sub V. So C sub P is greater than C sub V. And this is basically because at constant pressure, when we allow the system to expand, we have to include the energy for the expansion work. The other thing to note about C sub P and C sub V is these can be used for any process. These can be used for any process. The reason why they're called C sub V and C sub P for the constant pressure and constant volume is because that's how they're calculated. So the C sub V is calculated using a constant volume, and C sub P is calculated using a constant pressure. So this is just specifying how the derivatives were taken, but they're valid for any process. The other thing to notice is if we look at, say, C sub V, U, so we have the internal energy and we have temperature. These are properties, so these are thermodynamic properties. And so the C sub V and C sub P are calculated basically with thermodynamic properties. And so that means that C sub P and C sub V are also properties themselves. And so since they're a combination of thermodynamic properties, they're also considered properties. And so like other properties, that means that they depend on the state of the system. So specific heats are intensive properties. Their units are normally something like kilojoule, kilogram Kelvin, or in English units, they could be BTU, pound, mass, Rankine. So specific heats are intensive properties, and that means that they don't rely on this. They don't depend on the size of the system. So they're independent from the size of the system. So sometimes these are also given as a molar basis. So you'll see C sub V with a line and C sub P with a line. So remember, this line usually means that it's given on a molar basis. And so the units for these on a molar basis would be, say, kilojoules per kilomole degrees Celsius, or say kilojoules kilomole Kelvin. So just pay attention to the units. So when you use a specific heat, pay attention to the units and make sure that you're using consistent units in your problem. So now the question is, why do we want to, when would we use a specific heat? So basically we're going to use a specific heat if we have an ideal gas or a liquid. So basically we've already seen that, like, if you have water or say R134A refrigerant, you're going to want to get your internal energy or your enthalpy from the tables. But basically there isn't thermodynamic data available in table form for lots of different substances. And so if we have an ideal gas that it's not water or it's not a refrigerant, then we're going to want to use a specific heat to calculate our internal energy or our enthalpy, and also for certain liquids, which we're going to talk about that. I'm going to talk about that later. For this video, I'm focusing specifically on ideal gases. So let's look at an ideal gas. So first of all, for an ideal gas, we know that PV is equal to RT. And, well, let's also write down the equation for enthalpy. So enthalpy is equal to enthalpy is equal to the internal energy plus the pressure multiplied by the volume. And so if we look at this, we have PV here, and then we know that PV is equal to RT. So we can write this as the enthalpy is equal to the internal energy plus RT. And then for an ideal gas, the internal energy is a function of temperature only. So this is for an ideal gas. The internal energy is a function of temperature only. So basically now we have the enthalpy is equal to U plus, or the internal energy plus RT. We know that the internal energy is a function of temperature only. And then we have the gas constant multiplied by the temperature. So basically for an ideal gas, the internal energy and enthalpy depend only on the temperature. So they depend only on the temperature. So what this means is that C sub P and C sub V are also only depend on the temperature. So basically what we can do, if we go back to the original equations that I had for C sub V and C sub P, is we can say, so we have C sub V is equal to du dt as with constant volume, and C sub P is equal to the partial of H to T with constant pressure, so with the pressure held constant. So what we can do is we can replace these partial derivatives with ordinary derivatives, because these are a function of, basically these are a function of temperature only. So what we're going to get is d, so for this one we're going to get that du is equal to c sub v t dt, and this one is dH is equal to c sub p t dt. So I'm going to go to the next page and just rewrite these. So we have that du is equal to c sub v t dt, and dH is equal to c sub p t dt. So basically, remember, the reason why I could replace the partial derivatives with an ordinary derivative is because we were able to determine that basically c sub v and c sub p are functions of temperature only for an ideal gas. So what we can do is we can integrate these. So we get, for this one, we get that u2 minus u1 is equal to state 1 to state 2 c sub v t dt, and this is going to be units of kilojoules per kilogram, because I'm writing this on an as mass basis. So that's why I have the little, or the lowercase u. So this is kilojoules per kilogram, and then this one is H2 minus H1 is equal to, and this is state 1 to state 2, c sub p t dt. So now we have some relations for, so we know that, and this u2 minus u1 is delta u, and this h2 minus h1 is delta h. So now we have some equations that we can use to calculate delta U, or the change in internal energy, and delta H, or the change in enthalpy, for an ideal gas. And so this is basically assuming that we don't have a thermodynamic table available that we can just go look these up. So we're going to need to calculate them. And so in order to integrate these, we need to know what c sub v of t is and c sub p of t. And just to remind you, these only apply if you have an ideal gas. There are a few different ways that we can get these relations. First of all, there are analytical expressions for c sub v of t and c sub p of t given as third order polynomials. So we can basically look up an analytical expression for c sub v of t and c sub p of t. So if we go to our tables, notice how, so there's table A-2, and so table A-2A, we have this, says it's ideal gas specific heats of various common gases. We're going to talk about that in a minute. And then A-2B, we have ideal gas specific heats of various common gases at various temperatures. So if we go back up to this one was at 300 Kelvin, and down here, this one is at various temperatures. This is giving us a specific heat at various temperatures for various gases. And then if we go to table A-2C, we get this equation that gives us c sub p as a function of temperature. So we have this equation here that is giving us c sub p as an empirical analytical equation, and it's a function of temperature. And so we have constants in here for a bunch of different gases. And so basically, if you want to use this equation, you would just look up the constants for whatever gas it is you're using, and then you would plug this equation into your integration and integrate. And we'll look at an example of how you would do that in a minute. So notice that so we have this is only giving us C sub P, and so there's no value for C sub V. So we're going to see how you would get that in a minute as well. But one thing I want to point out is notice how this is giving C sub P with the bar, so this means that it's on it as a molar mass basis. So to get C sub P, we need this relation, so C sub P over the molar mass. So this is the molar mass. So this relation is good for low pressures, and it can be used for moderate to higher pressures as long as the gas doesn't deviate significantly from ideal gas. But we're going to see when we do an example that if we have, say, let's say that we're calculating the change in enthalpy. So we have state 1 to state 2, and then we have C sub P T dt. So we're going to take this equation, well, actually we're going to divide it by the molar mass. So we're actually going to take this equation, and we're going to plug it into our integration, and then we're going to integrate. And this is a pretty easy integration, but it's really time consuming. So this isn't the most practical way to do it a lot of the time. Another way that we can calculate, or we can get C sub P, we can just calculate C sub V or C sub P at an average temperature. So what I mean by that is, so let's go back to our equation. So we want to calculate this change in internal energy or change in enthalpy. So we need the C sub V or C sub P as a function of temperature. So basically what we can do is we can say, okay, well, over a small temperature change, then we can, and this would be maybe a few hundred degrees or less, and for some gases it's even more, we can just take the average temperature and then calculate or look up the average specific heat for whatever temperature it is we're interested in. So if we're getting the average specific heat, it's basically going to be a constant. So what we end up with is U2 minus U1 is equal to 1 to 2, and then we have C sub V average dt. And since the C sub V average is a constant, we can pull it out of the integration, so we get C sub V average 1 to 2 dt, so this is equal to C sub V average T2 minus T1. And we can do the same thing for the enthalpy, so H2 minus H1 is equal to 1 to 2 C sub P average dt. So then this is a C sub P average is a constant, so we pull it out of the integration, so we get C sub P average 1 to 2 dt, C sub P average T2 minus T1. So now it's just a matter of looking up what C sub V average and C sub P average are and multiplying them by the temperature difference to get the change in internal energy or the change in the enthalpy. So the way that we would look these up, let's just look at it. Let's go back to the chart. So now we want to look at A-2B. So for this table, we're looking at, so this is for certain gases. So we have air, carbon dioxide, CO, hydrogen, nitrogen, and oxygen. So let's say that we have a process where we have hydrogen, and the temperature change is, let's just say it's from 400 to 600. So what we're going to do is just calculate the average temperature. So the average temperature, 500 degrees, so we just add those together and divide by 2. And so then what we're going to do is take our specific heat for the average temperature. So if we were interested in C sub P, we would use 14.513, or if we were interested in C sub V, we would use 10.389. So you can see that this is a pretty significant simplification over using the polynomial expression. So one thing to notice about this table, at least in your book, is we only have information available for 6 different gases. So this information is pretty limited. And so another approximation that we're going to do sometimes is we're just going to assume that we can use the specific heat at room temperature. So for this chart, that's at 300 Kelvin. And so you can see that this chart has quite a few more values for specific heat, and there are lots of values for specific heat available online. So if we end up using this approximation, this is often denoted as C sub P naught or C sub V naught. So if we're going to use the specific heat at room temperature, go back to this, the way we're going to write our equation, and I'm not going to go through these integrations again because it's the same. The integration is going to be the same. We're just going to have a constant here that's CV naught and CP naught instead of CV average and CP average. So we're going to end up with, in the case of using CV naught or CP naught, we're just going to get U2 minus U1 is equal to CV naught, T2 minus T1, and H2 minus H1 is equal to CP naught, T2 minus T1. So really, we have 3 different ways to calculate the same thing. For this class, probably the best way is going to be using C sub V average or C sub P average, and that's because it's significantly easier to use those than the polynomial expression. The polynomial expression is technically going to be more accurate, but it's kind of an outdated method because it takes a long time to use, and with the amount of information available on the internet now, it's almost faster to just look up the C sub V or C sub P value that you need online than it is to go through and calculate it from the polynomial. So most of the time you're going to want to be using CV average or CP average. The times that you would use the CV naught or CP naught are when the data isn't available for you to calculate C sub V average or C sub P average, and that basically just means that you don't have the specific heat information available for different temperatures at the gas you're interested in. So now the question is, well, when is this approximation good? Because basically with this, when we're calculating the C sub V average or C sub P average or the C sub V naught and C sub P naught, this is an approximation for the specific heat. So let's draw a chart. So this is C sub P on a per mole basis and temperature, and this temperature is Kelvin. So let's look at how the specific heat varies for gases at various temperatures. So first of all, if we have a monoatomic gas, and this would be, so monoatomic gas is, say, argon, helium, neon, krypton, xenon. So I'm just going to make a list. So argon, helium, neon, krypton. The specific heat for these gases doesn't vary with temperature. So basically, you just end up with a straight line. So this would be argon, helium, neon, etc. So monatomic gases. So basically, if you have a monatomic gas, you can use one of these approximations, and your specific heat and hence your internal energy and enthalpy are going to be pretty accurate. If you have a different type of gas, like let's say you have hydrogen, that's going to look more like this. So you can see that hydrogen is going to vary with the temperature. Same thing with oxygen. Oxygen looks something like this. So this is O2. CO2 looks something like this. So basically for some of these gases, if you have a wide temperature variation, and this is, I should have put some numbers on here, so this is 1,000, 3,000 Kelvin. So let's say your temperature is changing from 1,000 to 3,000 Kelvin, and let's say you have gas that's not a monatomic gas, so you have hydrogen, oxygen, or carbon dioxide. These approximations probably aren't going to be extremely accurate because your specific heat varies quite a bit over that temperature range, but that's a temperature range of nearly 2,000 degrees. So if you have a smaller temperature range, like let's say you're in here somewhere, so let's say your temperature changes from like here to here, you can see that the specific heat, like the change in the specific heat is much smaller, so your approximation is going to be much more accurate. So sometimes if you have a small temperature change, you can often just use these approximations and assume that they're pretty accurate. If you have a large temperature range, your approximation might not be as accurate. And keep in mind as well, these we're already assuming that we have an ideal gas, and an ideal gas is already an approximation. So if you're using one of these approximations and it's something like this where it's only going to be off by a little bit, that's not really a big deal because your overall calculation for the internal energy and the enthalpy, or change in internal energy and change in enthalpy, is already off slightly anyway because you're already assuming an ideal gas. So you're only going to need to be concerned about these approximations not being accurate if you have a gas that has a wide variation with C sub P over the change in temperature, and you have a really large temperature change. And large temperature change probably means a few thousand Kelvin. So now let's look a little bit more at the specific heat and ideal gas relations. So we know that the ideal gas is equal to PV is equal to RT, and the enthalpy is equal to U plus PV. So we've already seen this. We can replace RT. We know that PV is equal to RT. This is for ideal gas. So the enthalpy is equal to U plus RT. So then what we can do is we can differentiate this. So we can say dH is equal to du plus R dt. So this dH is C sub P T dt, so we've already seen that. And we know this because we've already seen that dH is equal to C sub P T dt, and also du is equal to C sub V T dt, so we can plug that in right here. So basically C sub V T dt. So then this equation becomes C sub P T dt is equal to C sub V T dt plus r dt. And then if we divide this by dt, we get that c sub p is equal to c sub v plus r. So I've divided this divide by dt. And this is the gas constant. And remember, this has units of kilojoules, kilogram, Kelvin. And so basically this is our relationship between C sub P and C sub V. So C sub P, so basically so R, the gas constant, is equal to C sub P minus C sub V. And this can also be written on a as molar basis. So on a as molar basis, this would be Ru. So the universal gas constant is equal to C sub P minus C sub V. And so this is the relationship we're going to use if we have, let's say we have C sub P and we need C sub V, then we can use this relation to get C sub V. Or if we have C sub V and we need C sub P, we can use this relation to get C sub P. And also remember that C sub P is equal to C sub V over the molar mass, and C sub V is equal to C sub P over the molar mass. So these are some relations we can use to get either C sub P or C sub V from one or the other, and also on the as molar basis. And also the specific heat ratio, so you'll see this K. K is equal to C sub P over C sub V, and this is referred to as the specific heat ratio. And this is an ideal gas property. So this K will vary with temp, but not by a lot. And if we have a monatomic gas, which basically means that our gas is one atom, then this is essentially constant. So for a let's write this over here, for a monatomic gas, K is approximately 1.667. And for a diatomic gas, which means that we have two atoms, so an example of that would be hydrogen. So if we have, let's do air. So air is a mix of like nitrogen, oxygen, so N2, O2, CO2. Then at room temperature, K is approximately 1.4. And this is at room temperature, so if we have a different temperature, this will be slightly different. So now let's look at an example of how we would use all of this stuff. So what we want to do is we want to calculate the change in internal energy of air. So, and also let's take a step back. So we're going to, let's calculate the change in internal energy of air. So we have air, and we're going to say that it's, so T1, so initially it's at 300 Kelvin, and P1 is 200 kilopascals, and then it's going to be heated at constant pressure, so P2 is equal to P1, to 600 Kelvin, so T2 is 600 Kelvin. So basically we have air, and since we're heating it at constant pressure, I'm just going to assume that it's in a piston cylinder. So we have air, we're heating it, so we're adding heat, and it's starting at 300 Kelvin, ending at 600 Kelvin, and it's at constant pressure. So let's make some assumptions. First of all, we're going to assume that this is an ideal gas. And what we want to do, we want to determine the internal energy on a unit mass basis. So we want to determine, we want to determine the change in the internal energy. So we want to determine delta U. So let's put a question mark. And so first, let's do this first using the air table. If we go to table A-17, this is the air table, and we can look up U1 and U2. So U1, so at state 1, U1, well, the temperature at state 1 was 300 Kelvin, so U1 is equal to U at 300 Kelvin. So if we look that up on here, so 300 Kelvin is right here, and we have, so we want to look up U, so we're looking up the internal energy, so U is this 214.07 kilojoules per kilogram, and then this was heated to 600 Kelvin, so that is right here. U2, or the internal energy at state 2, is 434.78 Kelvin. So now we can, so I'm just going to put U2, well, so I'll put U1 first. So U1 is equal to 214.07, and this is kilojoules per kilogram, and then U2 is U at 600 Kelvin. This is equal to 434.78 kilojoules per kilogram. So now we can go put these back into our equation so we can calculate delta U, because now we know what U2 and U1 are. So this is equal to 434.78 minus 214.07, and this is kilojoules per kilogram, so this is equal to 220.71 kilojoules per kilogram. So using data off the table like that is going to be the most accurate way to calculate delta U, but the whole point of this section is, and specific heats, is, well, what if we don't have that data available? Because that data isn't available for a lot of gases that we're interested in. So now let's look at how we would calculate this using this polynomial equation. So we know that U2, well, delta U is equal to U2 minus U1, and this is equal to, so we're going from 1 to 2, C sub V T dt. So we need in order to solve this, we need this relationship between, or we need to know how C sub V is a function of temperature. So remember, one way that we could do that, well, there's two ways that we can do this, and we're going to do both of them. So we can either get the polynomial, so we can look at table A-2B, and we can get a polynomial for C sub P of T is equal to A plus BT plus CT squared plus dt cubed. So we're going to do it that way, but the other way we can do it is we can just assume that that we can use the average specific heat for C sub V. So basically we're going to use C sub V average. So let's start with this polynomial method. So delta U is equal to U2 minus U1 is equal to state 1 to state 2, C sub V T dt. So let's go see how we would get our information from this chart. So this is table A2-C, and we want to get, so we're looking for C sub V. Well, this table only has C sub P, but we can get C sub V because we know that C sub V T is equal to C sub P T minus the universal gas constant. So basically this is going to be, well, let's just get the equation first. So we're interested in air, so we need to find air, that's right here. So we're going to get our constants, so A is 28.11, B is 0.1967 times 10 to the negative 2, C is this, D, and then this tells us the temperature range that this is valid over, so, and then the percent, some percent errors. So let's look, so let's write down our equations. So C sub P, and this is per mass basis, of T is equal to A plus BT plus CT squared plus DT cubed. And then we have our values for A, B, C, D, etc. that we're going to get off the table. We also know that C sub V of T is equal to, and C sub V is what we want, so C sub V of T is equal to C sub P of T minus the universal gas constant. So this is equal to A minus RU plus BT plus CT squared plus DT cubed. And then we actually want, we don't want this on a molar basis, we want this on a mass basis, so we're actually going to end up dividing this by the molar mass as well, because C sub V is equal to C sub V over M. And but I think I'm going to do the math and then do that very last. So what we want to do, I'm going to calculate this on a molar basis or per mole basis first, and then I'm going to convert it into the mass basis. So this is 1 to 2, which is equal to, so C sub V T dt, and this is equal to state 1 to state 2, A. So I'm just copying over the equation I wrote down on the last page. So A minus universal gas constant plus BT plus CT squared plus DT cubed dt. So this is a pretty easy integration. This is just basically we get A minus RU T plus BT squared over 2 plus CT cubed over 3 plus DT to the 4th over 4, and then this is from state 1 to state 2. So basically we're going to end up with A, so we have A minus RU, and then we're going to have T2 minus T1 plus B T2 squared minus T1 squared over 2 plus C T2 cubed minus T1 cubed over 3 plus D T2 to the 4th minus T1 to the 4th over 4. So basically, I'm not going to plug in all the values because that'll take a while, but basically we know what everything is. We know what A, B, C, and D are because we just get those off that chart, and we know the initial and final temperatures, and we know the universal gas constant, so we just plug everything in, and if we do that we get that delta U is equal to 6,447 kilojoules per kilomole. But then we want this on a mass basis, so I'm going to divide this by the molar mass. So if I do that, the molar mass for air is 28.97 7. So I'm just doing delta U is equal to, this is equal, well, actually, delta U is equal to delta U over M, and M is the molar mass. So this is, the molar mass is units of kilogram per kilomole. So the kilomoles are going to cancel, and I'm get 222.5 kilojoules per kilogram. So if we compare that to the value that we got from our table values, 222.5 is really close to, it's pretty close to 220.71, and so 220.71 would be considered more accurate because we got our values directly off the tables. This one, using this polynomial, is an approximation, but this is a pretty good approximation. Now let's look at what we get if we used the average specific heat. So remember, this is one way that we can do this, assuming that we don't have table data. So if we have table data like this one, we just want to use the table data because that's going to make, it's going to give us a more accurate result. And so basically, if you have water, or if you have a refrigerant 134A, or if you have air that you can get off this air table, you're going to use the table. But if you don't have data available, like let's say you have nitrogen or helium or argon or some other gas, this is one of the approximations you can use to get your data. So the other way that we want to do this is, let's just go to the next page. So we have delta U is equal to U2 minus U1, and this is equal to state 1 to state 2, C sub P of T dt. This is C sub V. So the other thing that we can do is we can assume, we can use C sub V average. So remember, if we do that, C sub V average is a constant, so this becomes C sub V average T2 minus T1. So let's look at how we would get C sub P average. So we know that, like, let's just go look at the chart. We're going to be using A-2 again, only this time we're going to be using A-2B, where we have the specific heats at various temperatures, and we're interested in air, so that's this first one. And what we want to do is we want to look at the average temperature. So our temperatures are 600 and 300 Kelvin. So actually, it's hydrogen. So we have 600 Kelvin and 300 Kelvin. So that means that our average temperature is 450 Kelvin. So I'm just going to say T average is equal to 450 Kelvin. And that means that C sub V at the average temperature is 0.733 kilojoules kilogram Kelvin. So let's go back to slides. So we would just want to put the average specific heat in here. So delta U is equal to, well, so we looked up C sub V average, and it was equal to 0.733 kilojoules kilogram Kelvin. So if we put that into our equation for the change in internal energy, this is equal to 0.733 kilojoules kilogram Kelvin, and then multiplied by our temperature change, which is 600 minus 300 Kelvin. The Kelvins cancel, and this works out to 220 kilojoules per kilogram. So notice how this was significantly easier than our method using this polynomial method, and we ended up with pretty close to the answer we got using that method. And it looks like we actually got closer to the method that we used from the tables. So basically, this method using the average specific heat can be it can be accurate enough for a lot of things you're going to be doing. So basically, if you have information from the tables, that's going to be the best way to do this. If you don't, you're going to need to use the equation with a specific heat, and probably the next best way to do it is going to be using the average specific heat. But then if you don't have data to calculate the average specific heat, you're going to just use the specific heat at room temperature. So in this case, it would have been CV naught. And let's actually just calculate this with CV naught as well. So delta U is equal to, so if we use CV naught instead of the average specific heat here, this is just going to be CV naught T2 minus T1. So let's go look up CV naught. So we're going to get, and we would use the CV naught if we didn't have data for this for the whatever gas we're looking at whatever temperature we're interested in. And this table only actually has 6 gases, so it's pretty limited. So then we would get CV naught from this table, which has many more gases available. So here's air. So the specific heat so we want CV, so this is going to be 0.7188, or actually 0.718 kilojoules kilogram Kelvin, and this is CV naught. So let's go put this back into our equation. So this is equal to, so CV naught is 0.718 kilojoules kilogram Kelvin, so this is equal to 0.718 kilojoules kilogram Kelvin, and then multiplied by T2 minus T1, which is 600 minus 300 Kelvin. The Kelvins cancel. So this is equal to 215.4 kilojoules per kilogram. So this probably isn't nearly as accurate in a result as this one with the CV average, but depending on what you're doing, this could be adequate. So you need to think about, basically, the more accuracy you want. If you don't have data available, it's going to take more effort and time to solve your problem. So if this accuracy here is good enough, or if this accuracy is good enough, then you're just going to want to use the average specific heat, or the specific heat at room temperature, because it's much faster to get your result. Now let's look at another example. Let's say that we're heating gas in a tank by stirring it. So basically we have a tank and we're stirring it. So we're going to have some kind of shaft work. And let's say that this is helium, and it's an insulated rigid tank. So this is a way of saying that it's adiabatic. There's no heat transfer into or out of the tank. So this is an insulated tank. I'm just going to put that this means that it's adiabatic. And it's rigid, so that means the volume doesn't change. And it's helium. So let's just start writing down some things. First of all, the mass of the helium is 1.5 pound mass. The initial temperature is 80 degrees Fahrenheit. The initial pressure is 50 psi absolute. And we have some shaft work. And it tells us that the power rating is 0.02 horsepower, and it's operated for 30 minutes. So basically so we have this helium in this adiabatic tank. We're doing some shaft work, so we have work input, and we're raising the temperature and pressure of the gas. We have the initial temperature and pressure. We want to find the final pressure and the final temperature, so P1 and or P2 and T2. So let's make some assumptions. First of all, we're going to assume that this is an ideal gas, and we can do that because we have a high temperature relative to the critical temperature of helium. The critical temperature of helium, so T critical of helium, is minus 451 degrees Fahrenheit, and we have a temperature of 80 degrees Fahrenheit, so we can assume that this is an ideal gas. Also, since we have helium, and helium is a monatomic gas, we're going to assume constant specific heat. So we're going to assume that the specific heat is constant. We're also going to assume that this is a stationary system, so delta Ke is equal to the change in potential energy is equal to 0. And this is also constant volume, so V1 is equal to V2. This means that there's no boundary work. And we already have this an adiabatic system, so there's no heat transfer. So that means that Q in is equal to Q out is equal to 0. And we want to determine the amount of, well, actually, let's do our energy balance. So our energy balance, we have, I'm just going to say we have Q minus W is equal to delta U plus delta Ke plus, this should be capital, plus the change in potential energy. We've already determined that these are 0. So we just have that Q minus W is equal to delta U. Also, we know that there's no heat transfer, so Q is 0. So basically we have that the work is equal to the change in internal energy, and our only work is shaft work. So we have the work, and the work is being done to the system, so that means that our work is negative. So we have negative shaft work here is equal to delta U. So our energy balance is going to be that the shaft work is equal to delta U, which is equal to mass multiplied by U2 minus U1. We're not going to get U2 or U1 off the table because we don't have a table for helium. So we're going to use the specific heat, and we're going to assume that so we've already assumed that it's a constant specific heat, so we're just going to use the average specific heat. So this is equal to M CV average T2 minus T1. And actually, I'm not even going to use the average, because since we're assuming that it's a constant specific heat, I'm just going to use CV naught. And that's better for this case anyway, because we don't know what T2 is yet. So we want to use CV naught. And I'm just going to do a quick calculation. We can calculate the work, this shaft work multiplied by delta. So this is going to be equal to 0.02 horsepower multiplied by 0.5 hour, so 30 minutes is 0.5 hour. And then we need so 1 horsepower is equal to 2545 BTU per hour. So we can put this conversion in to change this to BTU. So 2545 BTU per hour over 1 horsepower. So if we work through that math, this is equal to 25.45 BTU. Basically, we have the work. What we're looking for, though, is, I'm just going to circle this. What we're looking for is T2 and P2. We can calculate T2 because we know, so we know the shaft work, and we know the mass because it's given. well, actually, let's look at this. Let's just rewrite this. The shaft work is equal to mass C sub V naught T2 minus T1. So we know T1, we know the shaft work, we know the mass, and we're going to look up the specific heat. So we can calculate T2. So the specific heat is equal to 0.753 BTU per pound mass degree F, and we're going to look that up on, that's from table A-2A, and this is the English table, so make sure you're looking at the table with English units and not the table with SI units. So the shaft work is equal to M C sub V naught T2 minus T1. And so we're just going to plug our values in and solve for T2. So we have 25.45 BTU. So we calculated this previously right here. This is equal to the mass, which is 1.5 pound mass, multiplied by CV naught, which is found on the table, so 0.5, or found on the chart for the specific heats. So BTU, pound mass degrees Fahrenheit, and then we have T2 minus 80 degrees Fahrenheit. So if we solve this for T2, T2 is equal to 102.5 degrees Fahrenheit. So basically we've increased our temperature from 80 degrees to 102.5 degrees Fahrenheit. The last thing we want to find is the final pressure, and we can find that from, we know this is an ideal gas, so we can use the ideal gas relation. P1V1 over T1 is equal to P2V2 over T2. We know, we know that V1 is equal to V2, so they just go away. And so now we have P1 over T1 is equal to P2 over T2. We know what P1, T1, and T2 are, so we're just going to solve this equation for P2. So we have 50 psi absolute over 80, and we need our temperature in Rankine, not Fahrenheit for this, so 460 to convert this to degrees Rankine is equal to P2 over 102 plus 460 Rankine, and then P2 is equal to 52.1 psi absolute.